Okay, today's study tip says, write a question mark in your notes or book next to items that are unclear. Ask for help from the instructor or other students to clarify your questions. This is just a little reminder, really, to put the question mark. So put a little mark and then go back later to clarify it by asking me, or you could go online, or you could find it in the book. There's all kinds of things you could do, of course. Watch the video again for that part. It's just a little note on the side of your book or your binder paper to remind you to go back and check it out later. Chapter 16, Respiratory System Part 2. Last time we did the mechanics of inhalation and exhalation. We learned about all those pressures and how air flows in and out of the lungs, and what if you had a hole in the lungs. So today we do Part 2 of the respiratory system. And we'll start with gases. A reminder, just like fluids, that they move from high to low pressure. Air is mostly, do you know this one? Tricky. What is the number one gas found in air? I don't think general public knows this. I think my kids do because they learn this in school, but I don't think most people know the number one ingredient of air is nitrogen. And we don't even use it. 78% nitrogen, 21% oxygen, a small amount of carbon dioxide, and water. Of course, the amount of water depends on the humidity. So the more humid it is, the more water is going to be in the air. We, of course, don't have very much humidity here in California. Each gas has a partial pressure, so that all of them total 760 millimeters mercury. So remember, that's the number we talked about last time. So what you do is you take the percentage, for example, nitrogen is 78%, times 760, and this will give you the pressure of 593 millimeters of mercury in air. So we say the partial pressure of nitrogen in air is 593 millimeters of mercury. Okay, partial pressure. So they all total 760. And this, of course, 760, remember, is assuming sea level, right? So it changes as we go up and down. Gases also have a partial pressure in liquid. So yes, as you know, there's oxygen in our blood, carbon dioxide in our blood, and you can measure the partial pressure there. Not nitrogen, though. Nitrogen doesn't go into our blood unless you're scuba diving or something like that, where it's pushing into the blood. Okay, this table is showing the partial pressures of gases in inspired air and alveolar air. So if we look at this picture, or this table, it's a list of ingredients, partial pressure in air, and then this upside down light bulb is supposed to represent the alveolar air. Okay, this is the alveolus. So the amount of water in the air is variable, like we just said, but no matter where you live, whether it's Florida or here in California, the amount that comes in the air that comes in goes over the nasal concha, down the throat, of course, through the trachea. By the time it gets to the alveolus, it's humidified, right? That's why we inhale the air, it goes deep down, so it's not dry anymore. So the partial pressure is 47 millimeters of mercury. The carbon dioxide is only 0.3 out in the inspired air, and then when it gets into the alveolus, there's a lot more. It's 40, so it goes up really high. Oxygen, 159, becomes 105, so there's less. Nitrogen, 601, is now 568, so there's also less. But see, the grand total is 760, same. Okay, so I need you to know these numbers, especially for the next page. This is a very good picture. Now you make a little note in your paper. It says, she says, this is a very good picture. We need to memorize all these numbers. Okay, so just start putting these in your head. Partial pressure of let's start here at the top. This is the lungs at the top of the page, then to the left atrium and the heart on the right of the page. At the bottom is the tissues, and at the left we go back to the right atrium and then back to the lungs again. So let's start the blood coming in from the pulmonary artery, remember, is deoxygenated. the partial pressure, when you see a big P and then a subscript O2, you say the partial pressure of oxygen. When you see a capital P and a subscript CO2, you say partial pressure of carbon dioxide. So the partial pressure of oxygen in this blood is 40. 40, what are the units? Millimeters of mercury. The partial pressure of CO2 is 46 millimeters of mercury. Okay, so these are just given numbers. And this would be at rest. Okay, then if you look inside the alveolus, the partial pressure of oxygen is 105, the partial pressure of CO2 is 40. So now that you've got these numbers, 40, 105, 46, 40, which way does oxygen go? Does it go into the alveolus or out of the alveolus? Well, you know this. Here's a little picture. Oxygen comes out of the alveoli. And the reason is because gases move from an area of high, 105, to low, 40. And this is going to keep, the oxygen is going to keep coming into the capillaries as it passes through the lungs until it comes to equilibrium. And there's one exception to this story, and it's right here. The first exception is the partial pressure of oxygen in the pulmonary vein is only 100, so not quite equilibrium. And your book gives the reason for that. It's not important to me. Okay, but it's almost at equilibrium, assuming that the flow of blood goes through slow enough in order to let all the oxygen come out. Okay, let's do CO2. The partial pressure of carbon dioxide is 46. Inside the alveolus is 40. So it's going to go high to low. So which way will the carbon dioxide go? In or out of the alveoli? It will come in, right? So it's picture CO2. You can see it coming in. How much comes in? Keeps coming in, keeps coming in, keeps coming in until the blood that leaves is the same pressure as the pressure inside the alveolus. So 40 and 40. Now this blood here at 140 then gets transported to the left atrium and the left ventricle and then out to the systemic arteries. Notice these numbers still the same, 140, just like we had at the top of the screen. Okay. Now it goes to the tissues, where inside of the tissues we have numbers. The partial pressure of oxygen is 40, partial pressure of CO2 is 46, and we're going to do the same thing now. We have O2 at 100 in the blood, in the capillaries, O2 at 40 inside the tissues. So which way will the oxygen go? In or out of the tissues? Will go in, right? Here it's showing in. Of course, you know oxygen now goes into the tissues to give the oxygen needed, of course, for electron transport system. And it's going to do that until the blood that leaves, over here, if you look at the number, it's equilibrium, 40 and 40. Carbon dioxide, let's do that one. It comes in at 40. Inside the tissues, 46. So which way will the CO2 go? Into or out of the tissues? CO2 goes out of the tissues. How much out? Until the blood that's leaving is at equilibrium with this blood in the tissues. So we have 46 and 46. Now this blood is going to leave and go to the right atrium, where it's going to be pumped and come back around. Notice the numbers are the same, 40 and 46. Okay, so this just goes around in circles. You need to pretty much memorize it, know which way things go, and all of the numbers. Okay, so now we write it down. Gas diffusion in the lungs. CO2 diffuses from the capillary at 46 millimeters mercury to the alveolus, where it's 40. Oxygen diffuses from the alveolus at 105 to the capillary, where it's 40. In the tissues, CO2 diffuses from the tissue at 46 to the capillary, where it's 40. And O2 diffuses from the capillary, where it's 100, to the tissue, where it's 40. And, of course, they diffuse until they reach equilibrium. Look good? Okay, we can alter all that gas diffusion, like during exercise, right? We have a real buildup of carbon dioxide, so that's much more. We have a real lack of oxygen, so that's a lot less. So we have a larger gradient, so we have a bigger high to low. And that's fine. Your body is going to make, as long as it makes equilibrium, okay, then the blood that leaves is going to be fully oxygenated if it's in the lungs, okay? Emphysema, so someone who smokes gets emphysema. They break up the alveoli, remember that? And so instead of having a nice round surface, they have little broken pieces. And so they've decreased the surface area for diffusion. So they will not have as good of diffusion of gas across the alveoli. Blood flow, this is called ventilation perfusion coupling. And that sounds like a fancy word, but it's not. You know it. Ventilation means, breathing. Perfusion means blood flow. So there has to be a coupling where the two things, the breathing rate and the blood flow, go together. Of course, you know that. If you breathe too fast and your blood's not moving quickly, then you're not going to have good perfusion and therefore no good diffusion of gases going back and forth. I want to see what else I have on this page here. So it says if the ventilation is low and the heart rate's too high, then you're going to vasoconstrict the pulmonary arterioles. Okay, so think about that. If ventilation is low, so you're not breathing fast, and your heart rate is that's not very efficient, right? You need the heart rate to go with the ventilation. That's like when you exercise, they both go up, right? And when you sleep, they both go down. So they need to go together. Well, if they're not going together for whatever reason, illness, something like that, then vasoconstrict, in this case, will vasoconstrict the pulmonary arteries. So what will that do to the flow? If you vasoconstrict, the flow goes down. So this slows the blood moving past the lungs. And then I just write here, because I'm out of space, the opposite is also true. So that would mean if your ventilation is high and your heart rate is low, you would have to vasodilate, because you need more blood to go past those lungs. And your body just does this to keep things together, okay? Continuing, this picture is showing Mount Fuji, I think. I think I want this for number 5. So let's do pulmonary edema first. Pulmonary edema, pulmonary means lungs. Edema, the fluid, like swelling. So you have fluid in the lungs. This could be for lots of reasons too. Might be inflammation, infection, something like that. Fluid or mucus in the alveoli would increase the distance for gas diffusion. Okay, so remember, we just have a little ways to go from the last lecture. We don't have far for the oxygen to travel from the alveolus. Remember, there's just a thin cell to pass, then into the one cell capillary. Boom, you're in. But if you add mucus to that, you now have a longer distance for the gas to diffuse. So it's harder for oxygen to get into the capillaries in the lungs, and it's harder for CO2 to get out, right? And then this is the altitude one. So this is a picture of the volcano. You go up really high. It's like 12,000 feet. So the altitude, there's less atmospheric pressure in Tahoe. So we did this last time. This changes the high to low diffusion. So you don't have the 760 anymore, right? So it's going to be, you have to inhale, make deeper breaths, right, in order to get the oxygen moving and carbon dioxide moving. Okay, so that changes the gas diffusion, changes the high to low diffusion. What do I have next? Oh, fun fact, the total surface of the alveoli in both lungs is the size of a tennis court. Yeah, plenty of surface area, huh? In your lungs, if you could spread it out, it'd be the size of a tennis court. Okay, here's a question. Sarah was very ill, and her roommate noticed that Sarah was hypoventilating, which is a slow, shallow breathing. There were even moments of apnea when her breathing temporarily stopped. Compare the exchange of oxygen and carbon dioxide in the lungs of Sarah versus her roommate, who was feeling fine. What effect will the gas exchange in Sarah's lungs have on the gas exchange in her tissues? Okay, so take a minute, go back to the picture that I really like, okay, and think about these answers. Okay, do you know the word, hypoventilate? To breathe slow, right? What's the opposite? To breathe fast is called hyperventilating. Have you heard of sleep apnea? When people stop breathing when they're sleeping. So you've heard of apnea. So comparing the exchange of oxygen, so what's the exchange like? Is she getting, see, she's not, is she getting enough oxygen? No, because she's not breathing, really. And so her oxygen levels have decreased, so she's not getting enough oxygen. Therefore, her high to low part, you know, if we go back to the picture, where is it? Here, this one. She doesn't have the 105, right? Because she's not getting enough oxygen. And because she's not exhaling, she's not getting rid of all the carbon dioxide. So this number is going to be higher or lower than 40. It's going to be higher. So she's going to have more CO2. So therefore, the blood that's leaving is not going to be 40 for the partial pressure of CO2. It'll be higher. And the amount of oxygen leaving the lungs is also not going to be correct. It's not going to be 100, right? 100, because this is not going to be 100. So then we don't deliver enough oxygen to the tissues, and we don't take away enough CO2. You can see how this is a vicious circle, right? So eventually, her oxygen levels start to get low, which we will see is not the most dangerous part. But in the tissues, if the CO2 becomes really high, that is the toxic part. So we'll talk about that in a minute. Okay, let's go back. Whoops, wrong way. Sarah, there she is. So it says, compare the exchange of oxygen and carbon dioxide. So we got that versus her roommate is feeling fine. What effect will the gas exchange in Sarah's lungs have on the gas exchange in her tissues? So there's not as much exchange in the lungs because we don't have that good high to low ratio, and therefore poor gas exchange in her tissues. And as we'll see, the carbon dioxide becomes toxic. What should Sarah's roommate do? What do you think's wrong with Sarah? Well, she's sick. Maybe she's taking drugs. We don't know. And so Sarah's roommate should do what? Pick up the phone. Dial 911. Yes, so this is very bad. And she needs help right away. Okay? Oxygen transport. Only 1.5% of oxygen is dissolved in the blood. The rest is carried by hemoglobin. You know that, right? Hemoglobin. So when we abbreviate hemoglobin, we write HGB. It has, as you recall, 4 subunits, each with a heme and iron. Here's the picture again. We have the 4 subunits, each with a heme group in the middle. So one hemoglobin carries how many oxygens? 4. Assume it's fully loaded in the lungs. It's going to carry 4 oxygens. Okay. I turn my page too. HGB is reduced hemoglobin. So when it picks up oxygen, the hydrogen comes off. So the hydrogen actually pops on and pops off. Okay, so it's called reduced hemoglobin. HGB plus O2 is called oxyhemoglobin. Okay, oxy, easy, oxygen. So when the hydrogen is on, it's reduced hemoglobin. When it jumps off and the oxygen gets on, it's called oxyhemoglobin. Here's the other interesting thing. The way hemoglobin is designed is if one oxygen binds, then there's a change in the structure so that those binding sites kind of become more open to allow hemoglobin greater attraction for the other 3. So remember, it holds 4, right? So if one binds, then pop, 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 they all pop on together. If we take a look at your plasma, remember plasma is you take blood and you remove the red cells, right? You get the plasma. And we'll make a container here with plasma and a container here with whole blood. And here this gas tank we set up so that the partial pressure of oxygen is 100 millimeters of mercury. We send the oxygen into the plasma and let it bubble through, and then we send it over to the whole blood and we let it bubble through. If you measure the partial pressure of oxygen here, it's 100. It's the same as the gas tank. Okay? But look at the number of oxygen molecules here. 1, 2, 3, 4, 5, 6. Okay? If we do whole blood, the partial pressure of oxygen is also 100. But that's just counting the little the little dots floating around. It is not measuring the amount that is stuck onto each hemoglobin. Of course, how many are stuck on each hemoglobin? 4, right? 1, 2, 3, 4. So if we measure the partial pressure of both of these, it looks like they're both the same, 100 and 100, and they are. But if you actually look at the oxygen content, here down on the bottom left side, we see that the left side has 0.3 milliliters of oxygen, whereas the right side, because of all the oxyhemoglobin, has 20 milliliters of oxygen. So this is how we carry so much oxygen in our blood. We have a little bit dissolved in the plasma, but tons of it is added on to each hemoglobin. And that's not actually measured. When we measure the oxygen content, we're not usually measuring the amount carried by the blood. Okay? Sorry. We're not measuring the amount. How do I say this again? When we're measuring the oxygen content, we're measuring the amount carried by the hemoglobin. When we measure the partial pressure, we're measuring the amount of free oxygen. Did I just confuse you? Listen to that again. More about oxygen. So the oxygen bound to hemoglobin. So now we're taking a picture and writing it down. The oxygen bound to hemoglobin does not contribute to the partial pressure of blood. Okay? In the figure, the partial pressure of O2 was 100 millimeters mercury with or without the hemoglobin. However, the oxygen content, total content, in the container with hemoglobin is much higher. And hemoglobin saturated, you need 4 to be saturated, is determined, of course, by the partial pressure of oxygen. So in that picture we had 100, which is full, pretty much. Remember in the lungs, that's what it is, right? But if we had more, higher partial pressure of oxygen, we would have more saturation of hemoglobin. And in Sarah's case, the partial pressure is lower, so you would have a lower hemoglobin saturation. All right? Okay, this graph is a classic physiology story, okay? Everyone has to learn this one if you take physiology. It's called the oxyhemoglobin dissociation curve. It's plotting 3 things, actually. So let's start on the left side. The percent oxyhemoglobin saturation. So this says 100, 80, 60, 40, 20. So if you can think of this as the hemoglobin is 100% saturated. So how many oxygens are on hemoglobin at 100%? 4, right? There's 4. And then this dotted line down below is 75%. So how many oxygens are on the hemoglobin here? 3. And then 50 would be 2. 25 would be 1. Okay? This at the bottom is the partial pressure of oxygen in millimeters mercury. And remember, in the arteries that leave the pulmonary arteries that leave the heart. Pulmonary. Wait a minute. This is the, shoot, now I have myself confused. This is the pulmonary, this is not the pulmonary, this is the arteries leaving off of the heart. The heart aorta has 100 millimeters of mercury. So looking at the picture, I was cheating and going back to the picture that I told you I really like, okay? This is the arteries leaving the heart going to the systemic circulation, have a partial pressure of 100. And then you get down to the tissues. Remember, the blood that's leaving the tissues has partial pressure of 40. So we go 100, 40, 140, back and forth. And one of the things that happens is this blue line, if you take a sample of blood, whole blood, and you look at how much is saturated, okay, how many oxygens are on the hemoglobin, and you compare it with the partial pressure. And you could do this with the experiment that we showed earlier with the oxygen tank. You could do that. You will see that the way the blood behaves is that it kind of goes flat for a while and then it goes zoom and it falls straight down. So it's not a straight line. And it's a curve, okay? So it's called a dissociation curve. So let's look at how much we have in the arteries is 100% loading, right? So coming off the heart, we have bright red blood. There are 4 oxygens on the hemoglobin. Then when we get to the veins in the tissues, right, we are down at 75%, saturation, which is how many oxygens? 3. Then we go back to the lungs, back to the tissues, back to the lungs, back to the tissue. As we do that back and forth, this is like normal, okay? There is only one hemoglobin, or one oxygen that comes off of the hemoglobin, right? We have 4, we have 3, we have 4, we have 3, we have 4, we have 3. That's a really interesting thing, because if there's any problems, like Sarah, who has a lack of oxygen, we have this then steep part here of the curve where we have lots of flexibility to have any problems with oxygen. Okay, so we still have 3 oxygens left to use. 1 down to the 50, 2 more down to the 25, right? So the blood is designed to not use a lot of oxygen at normal rest, but to have a lot left to give if you're exercising or if there's some problem. This is, over here on the right side, the oxygen content. So remember we talked about the fully loaded hemoglobin is 20. When you get to the tissues, it's 15. So this is the amount unloaded. Look at all this extra we still have though. 15 to 0, we still have all this extra space. Okay, what I want you to know about the curve is in this slide. Okay, so I know that's a lot to see that. So hemoglobin is almost completely saturated at 60 millimeters of mercury. So let's go back and look at that. Here, normally remember it's 100 when we leave the heart, but let's say it's like Sarah and she's not breathing well, we're down to 60. Okay, let's make it really bad. But if you go straight up and you look at the blood, the whole blood, you'll see that we're looking really good. We're still 90% saturated, even at 60, which is 40 less than normal. Okay, so we still have a lot of oxygen left. Okay, so it says that hemoglobin is almost completely saturated at 60 millimeters mercury. This is 40 millimeters mercury less than normal. Hemoglobin is saturated even if the breathing is wrong. So remember I told you the lack of oxygen is not the problem. It's the buildup of CO2 that becomes the problem, and we'll talk more about that next time. I think in general, the public thinks, oh no, lack of oxygen. We're big on oxygen, but really it's the CO2 that's dangerous. Second thing is that the unloading of oxygen occurs at a steep portion of the curve. So this allows for 25% of oxygen to be dropped off in the tissues. So the hemoglobin is still 75% saturated at normal tissues. This gives flexibility if the tissues need more than just 25%. Okay, so going back here, what I'm talking about is how we have this part here where we lose 1 oxygen, but then we have this steep part here where we can lose tons really fast. So any change goes below 40, easily go to say 30, right? And you lose a whole nether oxygen. Okay, another 25%. Okay, so we got it? Okay, I'm going to give you another question, see if you can manipulate this curve, okay? It says, Stefan has chronic bronchitis. This condition has increased the resistance in his airways and therefore decreased plasma PO2 levels. When PO2 levels are not normal, the oxygen hemoglobin curve shifts slightly to the left or the right. Which way would the curve shift in Stefan's case? And compared to a healthy subject, does Stefan need hemoglobin to easily release oxygen, means less saturation, or tightly hold oxygen, more saturation in his tissues? Draw the curve we would see in Stefan's blood. Okay, so this is the picture you could look at. So the middle line is the normal one, and then when there's a change in oxygen like he has, there's actually a change in the blood. It's really crazy. The hemoglobin changes, and so then there's a change in the curve that you have. It either shifts to the left or it shifts to the right. So I want you to think about this. Turn off the video, pause the show. Think about which way Stefan would move in order to fix his problem. Okay? Pause. Okay, so he has chronic bronchitis, and it says, therefore, decreased plasma PO2 levels. Okay, so he has a lack of oxygen, right? The lack of oxygen, he needs more to be dropped off, right? Since he has a lack of oxygen. So he's going to have a shift in the curve. To drop off more, how do I get a pen here? Do I get a pen? Let's do a pen. Ballpoint pen, felt tip pen. Okay, let's do, let's go up to, let's do 90. Okay, let's go up to 90. And here we are at 90. Okay. And then we're going to go down to, let's say, 40. Here. 40 here, 40 here, and 40 here. Let's make him even worse, though. Let's take him down to 30. Okay? 30, 30, 30. Here's normal, right? Which shift would give him more unloading? Okay, so remember, we're going to start at the top. Let me put my pen back. My arrow. Okay. Start at the top at 90. Say the left curve, okay, takes him down to 70. So we go 90 to 70, 90 to 70. That's dropping off how many oxygens? If you go from, well, actually, it's not 90, right? Look at the top here. This number is like 99% saturated. Okay, so from 100% saturated down to 70%, we drop off like 1, right? Normally, a normal curve, we would drop off, I don't know, 1.5 if we were that bad, right? But going from on the bottom line here, we're fully saturated, go all the way down, we've dropped off at least 2, right? We're beyond 50%, now we're down to 45. So this top shift to the left curve dropped off 1 hemoglobin, but a shift to the right curve dropped off 2. Do you see that? Because it's steeper, goes down further than the shift to the left. So which one would be more beneficial for him? A shift to the left, where we drop off 1, or a shift to the right, where we drop off 2? Shift to the right, because he has a lack of oxygen, right? So we need to drop off more. So the other thing we can look at in this curve is this curve also, besides a lack of oxygen changing these two curves, also a change when there's a change in the pH of the blood. As you remember, pH of the blood should be 7.35 to 7.45. So in this middle line, which is the normal line like we just saw, this shows the pH of the blood at 7.4. If it becomes more acidic, 7.2, you'll get this shift. And if it becomes more basic, you'll get this shift. So he's probably more acidic, and so another reason why you're going to get this change in the hemoglobin. And this just happens, this shifting thing just the body naturally does. Okay? So this is called the Bohr effect. A shift to the right, which is what we decided would be beneficial for him, is to decrease hemoglobin saturation and increase oxygen unloading. It will happen if the partial pressure of carbon dioxide is high, which also means there will be a low pH, or increased temperature, so a fever, that would happen. There will be a shift to the left if we want to increase hemoglobin saturation and decrease oxygen unloading. It will happen if there's a lack of CO2, or increased pH, or hypothermia, decreased temperature. Okay, so you'll just have to memorize these. You can try to practice some more, like why would it be beneficial to go left and right. Okay, carbon dioxide is the next part of the story. It's a big part of the story. I keep mentioning it to you. Now we're actually going to get to it. 7% of carbon dioxide is dissolved in the plasma. Is that more or less than the oxygen? What was the oxygen number? Do you remember? We said it was 1.5. So we carry more CO2 in our blood. 20% of it is bound to hemoglobin to make carbaminohemoglobin. Try saying carbaminohemoglobin. So remember, hemoglobin carried everything for oxygen. It only carries 20%. You may not even have known this, that it carries carbon dioxide. That leaves 72, 73% is converted into bicarbonate ions. So this is the equation to know, love, and be. And it's very important for the next lecture, so I want you to memorize it today. It says carbon dioxide plus H2O will be converted into H2CO3, which is called carbonic acid. So I want you to say carbonic acid and write H2CO3, which then dissociates into hydrogens and free hydrogens and bicarbonate ion. HCO3 minus, you say bicarbonate ion. And there is an enzyme that does this called carbonic anhydrase. It's the enzyme for this reaction. This reaction, double arrow, goes left to right and right to left. In your tissues, where you pick up CO2, is where this reaction will go to the right. And then then it carries this bicarbonate ion to your lungs, and at your lungs this reaction goes opposite way to the left, so that you make the CO2 again, and you exhale. And then we go around to the tissues, we pick it up, exhale, okay? So CO2 plus water becomes carbonic acid, dissociates into hydrogens and bicarbonate ion. The equation to know, love, and be. Next is the brain stem respiratory centers, little anatomy review. Do you remember these? The midbrain, the pons, the respiratory stem, brain stem respiratory centers, pneumotaxic area, apneustic area, rhythmicity center area, the medulla oblongata. I need you to remember all those, okay? Chemoreceptors measure arterial PCO2. Okay, partial pressure, carbon dioxide. You have chemoreceptors, remember? A little increase, tiny bit of just 5 millimeters of mercury for CO2 causes an increased respiratory rate. Now, if you changed oxygen a little bit, 5 millimeters of mercury, no big deal. But 5 millimeters of mercury for CO2, big deal. We're very sensitive to the CO2, so we will breathe faster. A high level of CO2 is called hypercapnia. Hyper means high, capnia means referring to the CO2. A decrease in CO2 causes a decreased respiratory rate. This is called hypocapnia. Okay, to have a decreased CO2 is called hypocapnia. We also do measure partial pressure of oxygen with chemoreceptors. There are receptors in the carotid and aortic bodies. They are triggered by very, very, very low partial pressure of oxygen and responds, of course, with increased respiratory rate. Right? So if you have a lack of oxygen, you're going to breathe faster. And of course, the opposite is also true. If you have too much oxygen, you would breathe more slowly. And finally, the last thing and the most important thing, which is the big topic for the blood acid-base lecture next time, is arterial pH. So we do measure pH with chemoreceptors. Hydrogens stimulate an increased respiratory rate. So you have lots of hydrogens, it's very acidic, you need to breathe faster. And the opposite is also true. If you have a lack of hydrogens, you're going to breathe more slowly. Okay? We are done.